The observable universe is structured like a massive, interconnected web. Galaxies clump together along dense filaments, but between these glowing threads lie massive expanses of darkness. We call these empty regions cosmic voids. When astronomers measure the actual contents of these voids, they consistently find a severe material shortage. These regions contain roughly 60% fewer baryons, the particles that make up ordinary matter, than the cosmic mean. The standard model of cosmology attempts to account for this near-total evacuation by adjusting parameters for baryonic feedback and galaxy formation efficiency. It requires a significant amount of manual tuning to make the math match the emptiness. But the missing mass isn't the only anomaly. Telescope surveys monitoring weak gravitational lensing, like DES and KIDS, detect significant negative convergence inside these voids. Light rays actually diverge as they pass through. Right now, standard cosmology relies on separate modified growth statistics and specialized feedback prescriptions to account for these discrete phenomena. The model requires multiple ad hoc mechanisms to explain both the empty space and the divergent light. Physicist Satish B. Thorway recently published an alternative mathematical framework that approaches the problem from a different angle: dynamic vacuum field theory, or DVFT. This equation defines the vacuum as a single, unbroken, complex scalar field. Under Thorway's framework, the vacuum itself is the sole dynamical substrate of the universe. DVFT defines cosmic voids as actively repulsive topological structures, gravity hills that physically push mass away. Thorway proposes that this single geometric mechanism derives the immense emptiness of voids, the diverging light paths, and extreme optical transients, without requiring any mathematical fine-tuning. To understand how these repulsive regions form, we have to track the rapid evolution of the early universe. As the universe cooled, this single scalar field underwent a sudden transition known as a tachyonic rolldown. This rapid rolldown was followed by a Kibble-Zurek freeze-out. The sudden drop in temperature locked the state of the scalar field into place before it could reach a uniform equilibrium. The freeze-out fractured the continuous vacuum into distinct, isolated phase domains separated by sharp boundary walls. Each isolated domain is categorized by an integer winding number. The field rules dictate these integers must be positive or negative. This initial distribution of winding numbers created a permanent structural scaffold. According to DVFT, this microscopic topological fracturing set the blueprint for the macroscopic evolution of the cosmos. This equation defines the effective gravitational potential as a function of the vacuum amplitude. It reveals how gravity emerges directly from the vacuum substrate. Domains with a positive winding number cause a localized depletion in the vacuum amplitude. This generates a negative potential, forming an attractive gravity well, the regions where matter clusters to form galaxies. The opposite occurs in domains with a negative winding number. The vacuum amplitude is locally enhanced, creating a positive potential and forming a repulsive gravity hill. Because the amplitude is highest at the center of the hill, the vacuum pressure gradient generates an outward acceleration. The gravitational force points entirely away from the negative domains and directly toward the positive ones. The sign of the winding number is the sole determining factor. A positive integer dictates a galaxy-trapping cluster, and a negative integer creates a void that repels all baryonic matter. When we project this mechanism theorward over billions of years, the kinematics of these negative gravity hills scale up directly to the massive cosmic voids we observe today. The outward acceleration vectors function as a continuous cosmic pump. Baryonic matter that would normally drift into these expanses is flushed out of the red hills and compressed into the surrounding blue filaments. This constant geometric expulsion produces the observed 60% baryon deficit. The physical topology pushes the matter out, bypassing the need for complex reionization tuning. This simulation demonstrates how the physics of the hill apply to the trajectory of light. When parallel photon paths enter a negative hill region, the repulsive space forces them to diverge outward. This equation for negative convergence shows why light diverges inside a hill. Because the effective potential is structurally greater than zero, the math naturally yields the results seen in telescope surveys. Through local vacuum gradients alone, DVFT reproduces the divergent lensing profiles recorded by DES and KIDS, doing so without altering the established laws of general relativity. The physical consequences of this model extend to the boundaries of the voids, the sharp interfaces where the baryon pore hills touch the dense gravity wells. In this theory, the boundary between a positive and negative domain is highly unstable. When opposing topological structures meet, they trigger rare annihilation events. Astronomers have tracked exceptionally bright flashes called luminous fast blue optical transients, or LFBOTs. The DVFT framework identifies these transients as the visible signature of these defect annihilations. This energy equation accounts for the massive luminosities observed in LFBOTs. The physical release of one of these collisions produces exactly the output required to match the data. This interface mechanism explains why LFBOTs are typically found far from host galaxy centers. Because these annihilations occur at the boundary between a dense well and an empty hill, they naturally take place in baryon pore regions away from the galactic core. Standard astrophysics models rely on high-velocity runaway stars to explain these locations. DVFT predicts these extreme spatial offsets generically as a function of the primordial defect network. This matrix compares the theoretical economy of DVFT against the standard model. A single cause, the defect hill, accounts for the missing baryons, the diverging light paths, and the spatial offsets of optical transients. We can trace this economy to one final pillar. This map of the cosmic microwave background contains a distinct temperature decrement known as the CMB cold spot, which aligns with the massive Eridanus supervoid. The mechanics of the gravity hill generate a positive effective potential. Through the Sachs-Wolf effect, this potential dictates the temperature drop observed in the cold spot without requiring exotic topology. These four distinct cosmological anomalies all emerge directly and automatically from the underlying geometry of a single vacuum substrate. But a robust scientific theory requires testability. The DVFT framework makes specific, parameter-free predictions that upcoming multi-messenger surveys will soon test. The Euclid mission will map void lensing stacks with unprecedented resolution. DVFT predicts these new maps will trace a logarithmic profile that matches the gravity hill potential. Similarly, deep sky sweeps by radio arrays are expected to detect distinct phase twist residuals in the velocity fields of hydrogen gas located at the boundary lines of these voids. While standard cosmology remains the current standard, DVFT's relational framework offers a unified mathematical architecture. Upcoming observations will provide the data necessary to prove or falsify the physical existence of the gravity hills.